All right, I think I should be live now. Let me know in the chat if you can hear me and if the levels are fine, please. And I'm just going to assume that the levels are fine. I'm just going to start talking. So yeah, hi. Yeah, doing a live stream again after a long, long time. I think the last one I did was almost a year ago. Yeah, and the reason for that, as you probably know, is that I've been working on this Erica Synths collaboration, which recently wrapped up, which is great news because it means that I have some free time again and I can do things like this, which is a good thing. Yeah, happy to be doing these again. A few words of like kind of explaining like what this is, like if you haven't seen this format before and how it works. So basically, what I do in these streams is I kind of do what I do in my videos, but like kind of more free form and interactive. So you can send me questions in the chat if you have any trouble understanding what I'm talking about, and I am going to design a circuit with you, basically. That's how it's gonna go. And most of that work is going to happen in a circuit simulator, simply because it's like easiest for me to explain stuff and show it to you. And also, I'm not going to go into detail about the basics. So I'm just assuming like a kind of base level of knowledge on your part when it comes to like voltage and current and resistance and voltage dividers and stuff like this. So if you've watched my videos before, then I'm assuming that you know about these things. Okay, and if you are having trouble, then I think you can basically just turn to the chat and ask people there, and they're going to be able to help you, hopefully. Also, I'm going to take regular breaks within the stream to kind of address stuff in the chat that you couldn't clear up, or you know, any questions directed at me. I'm going to try and answer them as they come in. All right, with that out of the way, let's talk about what we are trying to design here. And as you can see from my title sheet, the topic is going to be envelopes. More specifically, we're going to try and design an ADSR envelope. And the reason for that is because that has been bugging me for quite a while, because I already have a video on an envelope generator, and it also says that it's an ADSR envelope generator, but the ADSR is put into quotes. And the reason for that is that it wasn't a real ADSR. It was kind of like a fake ADSR envelope. So I did some things to approximate a true ADSR, but you know, it still wasn't the real deal. And I really like ADSR envelopes for the music that I make, especially for like acid bass lines. ADSR envelopes are like really instrumental. And so I really wanted to have a proper ADSR kind of in my arsenal of circuits. And yeah, so I mean, before we can kind of like go into the simulator and work on that, I guess we have to define what an ADSR envelope actually is. So if we talk about envelope generators first, like without the specification, we can basically say that an envelope is a device that receives a trigger or a gate, basically, for example, from a keyboard or from a sequencer. And then in response to that gate or trigger signal, it outputs a rising and then falling voltage. And that rising and falling voltage can then be used to control other modules with it. So for example, a filter or a VCA, a VCO, like whatever accepts a control voltage signal, like that you can use it for. And yeah, so that's envelopes in general. But if we talk about ADSRs specifically, then it gets a little bit more complicated. And to kind of illustrate this, I have drawn up this little curve here. I hope you can see it. Let me know. As you can see, this curve is supposed to be the output of a true ADSR envelope generator. And as you can see, this curve is split into 4 parts. So we have the attack phase, we have the decay phase, we have the sustain phase, and then we have the release phase. And those 4 phases are like kind of like distinct from each other. And we can wait, let me check. All right, I think my preview here is too late. So yeah, I hope you can see the illustration, but I think someone in the chat said that you can. So I'm just going to pretend that you can. Right. So again, back to this shape. Again, 4 phases. And the way that it works is that the curve starts whenever there's a key down event. Like in our example, like in my example, I'm assuming that we have a keyboard connected to our envelope generator and that pressing on the key sends a gate signal to the envelope. And at this point in time, basically, we imagine that someone presses a key on the keyboard. And then what the envelope generator will do is it will enter its attack phase. And in that attack phase, it will push up the output voltage, right? So the output voltage will slowly rise up until it reaches a peak, which you can see here. That peak is kind of roughly standardized. I think in Eurorack systems, it's mostly like 8 volts or something like that. So that peak is always going to be the same. I mean, not always, we're going to get to that, but generally the attack phase ends when the envelope reaches kind of this peak, which we're going to assume to be 8 volts. Once the envelope has reached this peak, then what will happen is that the attack phase will finish and we will enter the decay phase. Now, the decay phase is basically the drop from the peak down to the sustain level. And we'll get to the sustain level in a second. But yeah, this decay phase is basically just dropping down from where the attack ended up. And yeah, like I said before, the decay is the drop from the peak down to the sustain level. Now, the sustain level is a kind of it's not a time setting, but instead it's like if we talk about voltages, it's like a fixed voltage level, right? So here I've drawn it to be like in the middle. So if we assume that the peak is 9 volts, then we could assume that the sustain would be 4.5 volts in this example. So we press the key, the output rises up to 9 volts. Once it hits 9 volts, it drops down to half that, 4.5 volts, and then it stays there. And that's why it's called sustain. It stays there until we let go of the key in our example, right? So we press, voltage goes up, voltage goes down, voltage stays at the sustain level until we let go of the key, and then finally the voltage drops, and this is called the release phase, right? You release the key, and basically after you release the key, then we run through this phase, which sees the envelope's output voltage drop down to the initial level again, right? This is how a proper ADSR curve would look like. Any questions about that? Is that unclear, or is it clear for everybody? Oh, somebody asked in the chat if this will be available after the stream has finished. So the way that I do it with these streams is that while I do them, they are public, but afterwards I only make them available via Patreon. So yeah, that's how that works. All right, so James says, very clear, good. That's great. Then I think we can jump over into the simulator. Because, or not because, right, to explain like where I'm starting from. So basically in the video that I've made on the envelope generator, I started out with an attack release envelope. And I don't want to stop before that because that would be a bit boring. So instead, we are going to take that as our jumping off point. So we'll start with a simple attack release envelope generator. Now, this is a very simple circuit. This is also very stripped back, so there's no buffering, there's no input buffering, there's no output buffering. This is really the bare bones of an attack release envelope generator. And the way that this works is basically over here. This thing is basically how I simulate like a keyboard in the simulator. So the idea is if I click on this, it's like a key down event. If I click again, it's like a key up event. So I'm pressing down and then I'm letting go of the key. And the way that this works is basically if I flip this switch, we connect it to this voltage, and then a current will flow through this diode, through this potentiometer, which is set up as a variable resistor, and into this capacitor. And it will fill up the capacitor. And that means that the voltage at this point will rise. And then when I flip this back again, so that would be equivalent of letting go of the key, then basically we allow the charge inside the capacitor to leave through this potentiometer and this diode and flow to ground over here. And just to prove to you that that's actually what happens, let's try it. So key down, key up. And down here you could see what happened. I'm going to do it again, and then I'm going to stop the simulator so that we can look at it for a second. All right, so here's that shape. You're going to notice that this is curved. This is not straight. You know, like in my illustration here, I've shown you straight lines. Here we see curved lines. The straight lines are more of an abstraction. So I know that there are some envelope generators that do like the linear curves. We're going to stick to this rounded version. But, you know, for all intents and purposes, it's like kind of the same thing. Right. So with an attack release envelope, we basically only have, well, we have three phases, right? What we have is we have this attack phase, which we enter when we press the key. And then we actually have a sustain phase, you know, like it's still going up a bit, but if I had waited a bit longer, at some point the capacitor would have been charged up to the input voltage to 5 volts, and then would just stay there until I let go of the key, right? So you could say that this is actually kind of a crude attack sustain, release envelope. With the only sort of thing is being that the sustain level is always going to be the maximum voltage in this system, which would be 5 volts. If we increase this to 12, it would be 12, but we have no way of like changing the sustain level by messing with any controls. Like we only have controls for the attack and the release phase. There's no control for a sustain level. So yeah, that's a very, very, very basic little envelope generator. And this is fine for what it is, so we can use that. The problem with it is that we don't have a decay phase and we cannot set the sustain level. So these are basically the two things that we would like to add. And with my previous envelope design, we sort of had those things, but not in full, and that was because I was missing a kind of very crucial component. And I figured, like, to make that more clear to you, I'm going to introduce a very very primitive version of that component to you, which is a SR latch or SR flip-flop. And I'm not sure if you all know what that is, so I'm going to just start at the bottom here. So a SR flip-flop is, I think it's probably the simplest type of flip-flop there is, which is basically a device that can store a bit of data. Right, so this is the most basic building block of like digital logic, basically, or digital memory. And we don't have to care too much about like the setup and how this works, like how this works internally. Like we just need to know like what these controls do and what the outcome is. So like I said, the SR flip-flop is a device that stores 1 bit of data. And I think this state is wrong, right? So I just reset it like this is the actual normal initial state. So the SR flip-flop has 2 inputs. This is where it gets its name, SR, because it's set and reset. And the flip-flop has 2 outputs. It has a regular output and it has an inverted output. So the relationship here is basically just that this is always the opposite of whatever the output is. We can kind of ignore this. We won't be needing the inverted output, but you know, I put it here explicitly just for to make it clear that that exists. Right. And the way this works is basically very, very simple. Right now, this is the initial state. The flip-flop is kind of storing a 0. You can see here, we have 0 volts at this output. That means this is a 0, like a logic 0. And we can change that if we toggle this control, this set control. If I toggle this one, then it doesn't work. Oh, because I stopped the simulation. All right, let me try again. If I push the set button, boom, you can see that the output is now on, the inverted input is off, and I've already flipped the switch, the set switch again, and the output is still on. So basically we told the flip-flop, hey, please toggle your state. Please go from on to off, right? That's what we tell it by clicking on set. And we can now, or let me put it this way, if I now toggle set again, nothing happens, right? Because the flip-flop is already kind of set to a 1, like we already have a 1 as an output. And so it says, well, I'm already 1. What do you want from me? I'm not going to change anything about that, right? So whatever we do here, it doesn't matter. The flip-flop puts out a 1. And the only way to get it back to 0 is to toggle the reset switch. So as you can see, I toggled it, and now this output dropped down to a logic 0. And we can do that, you know, indefinitely. And again, here with the reset pin, it doesn't matter like how often I toggle it. When the flip-flop is already off, the flip-flop stays off. Nothing happens. And now you're probably wondering why I tell you all this. Like, what do we need this for? What is this flip-flop good for? Well, if we go back to the simple attack release envelope, then we have kind of a difficult problem here. Or, I mean, right now it's not obvious, but it will become obvious that it's a complicated problem. So basically, if we look back to our waveform, we said that we want our envelope to kind of react to the fact that it reaches a peak level, right? So the envelope, after reaching a peak, should enter the decay phase. So in this envelope, that's not an issue simply because we do not have a decay and a sustain phase. So we don't need to know when we've reached the peak. But to actually implement this, like to get this logic that we rise, we reach the peak, and then we drop into this circuit, we need a way to detect that we've reached the peak. And this is actually where this flip-flop comes in. Because you might already see how that works, right? So if this thing is off, this would be before we press the key, the output is also off. So it wouldn't be charging our capacitor if we put this in front of our envelope, right? And then once the trigger comes in at the set input, it would trigger the flip-flop on. It would then start charging our capacitor. And we could then wire our reset to our capacitor voltage here, right? Because as soon as this reset pin goes high, or high enough, we're going to get to that in a second, then basically it would switch off this flip-flop, right? That's the basic idea. Send the trigger into the set input and then connect the envelope's output to the reset so that the envelope kind of switches itself off once it has reached the peak level. That's the plan here. And by the way, this works because a flip-flop kind of has a threshold at both of its inputs that determines like when it considers a signal as a logic 1 or a 0. So in this case, if we wired the output of the envelope back to the reset pin, then basically what would happen is that this reset would only get triggered after the output has passed a certain threshold. And that is the way that we know when we've reached the peak, and then we can start doing something else. And if that was confusing, I completely understand. So we are now going to look at how I've implemented this in the simulator. So, wait, let me discharge this. Boom. Okay, so as you can see, what I've done here is I have basically taken this AR envelope and I've cut away the release phase. So I've removed this and I've only implemented the attack phase after this SR flip-flop at the input. And I have to discharge this again, sorry, boom. Okay. All right, and the way that is set up is exactly like how I just described it. So basically, we have our input here. Again, this is our trigger. This is what we used here with the attack release envelope to trigger the envelope. We have that again over here, and then I've put a high pass filter here, and I've put a high pass filter here because this is something that I should have told you before. I'm very sorry, I forgot to tell you. So with these flip-flops, we have a little bit of a limitation. So this state, which we see right now, where the set is 1 and the reset is 0, is a valid state, right? This flips the flip-flop into its on state. Now, what's an invalid state is actually this. If set and reset are active at the same time. Why is that invalid? Well, the main problem, I think, is that it is kind of difficult, like when these go 0 at the same time, it's kind of difficult to predict like what the output of the flip-flop is going to be. And so basically what we say is this state, oh, I'm also just seeing that both are 0 now. That might also be a problem. But yeah, so generally like what in electronics, what the rule is for SR flip-flops is that you should not have a situation where set and reset are 1 at the same time. It's just a state that you should avoid. And to comply with that, basically what I've done here is I put a high-pass filter in front of the set input. And I've put this high-pass filter there because now whenever I flip this on, we just get a short voltage spike at this point and it instantly goes down to 0 volts again. So that way we can make sure that set and reset are not, or hopefully are not going to be 1 at the same time, right? Because this is only going to be a very short spike. And here, like, it takes a while until this goes high, so we should be in the clear with this. That's why I've put the high-pass filter here. All right. And then everything else is basically just how I described it. So we have our output here. That is the same output as this one. So it's not the inverted output, but instead it is the regular output, this one. And we've connected this output through a diode and a potentiometer to our capacitor. And so what will happen when this flip-flop switches on is that we charge the capacitor from the flip-flop, like Current will flow through here, through the resistor, and into the capacitor. And it will charge it up. And this means that the voltage at this node will rise. And because I've connected this node to the reset input of the flip-flop, at some point, the flip-flop is going to turn itself off. Now for these gates, right, I've set the high logic voltage, which I think is identical to the supply voltage in this case. I've set that to 12 volts. And in this simulation, what these gates do is they consider an input a high level input when it's half of this high level voltage. So that means that whenever the voltage here at the reset input is 6 volts or higher, then the flip-flop will shut itself off. Right, that's the theory at least. So let's see if this actually works, right? Okay, so I'm going to trigger this thing. Boom. You saw that? So basically what happened is I turned the flip-flop on, it charged the capacitor, and then when this, wait, let me put a little output here. I'll put a little output over here, boom, and I will show you, oh no, I'll show you the voltage at this point, boom. Right, so we can see, all right, that's because the capacitor is leaking, but you know, it used to be 6 volts. Right, so let me reset this, boom. That's what this switch is for, by the way. It's not really part of the circuit. I just have it here for convenience to discharge the capacitor instantly. So if we go again, I flip this on, we can see that the cap charges, the voltage rises, and boom, 6 volts. And that means that the flip-flop now turned itself off. Let's try it again. I'll trigger the flip-flop, we charge the cap, the voltage here goes up, 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 6 volts, boom, turns itself off. That is how that works. And this is basically how we've implemented the attack phase, and now we know when the attack phase is ending, right? Now you might say, well, this is 6 volts. Earlier you said envelopes should stop at 8 volts. Doesn't really matter, we'll get to that in a second. But what we've now implemented is basically this, and we know when we want to enter the decay phase. So this is already super, super helpful, because in my previous design, like in the design that I had in my video, we had no awareness of a peak. Like we didn't know when that was reached. And so with this SR flip-flop, we do have a kind of a concept of this. Because whenever we reach the peak, we know that this output is going to go low, which is going to be super helpful in a second. But first I want to know if there are any questions. Let me check the chat for a second. Charging a cap in voltage given exponential return and constant current given linear. Yes, we could actually in the end change stuff about the envelope to make it linear, but this is, we're going to stick to exponential for a second. Sauerkraft asked, how long is this stream? I guess it's going to be around maybe 90 minutes in total. And that's what I'm aiming for. And then Rolfian says, this state can also lead to uncontrolled oscillation. Yeah, I think you're referring to the state where you have both turned on. And I think you're right, like with reword components, that is what can happen. Oh, yeah, Computing Brain asks, can you elaborate on the uncontrolled oscillations? I think I saw it in the simulator already, but I'm not exactly sure how that happens. Maybe if I reset now? No. Oh yeah, I think you could see it there for a second. Reset. I'm not exactly sure what's going on with these gates and how they interact, but I think that's right. I think this state can lead to weird behavior. So we should just avoid that. Oh, sorry, I didn't show you the... No, I did show you that. Okay. All right, and then Bastionix asks, if I may ask, is it cool to use a regular gray diode instead of a signal diode for the VCO core? Well, the problem here with the diode is you want a diode that kind of reacts fast. And for that, traditionally, the signal diodes are best. So it's gonna still work, but you might have some weirdness when it comes to the pitch or the volt per octave tracking. And then Steiner Andreas says, I think you need the AND-based SR latch for the oscillations. You might be right. But good. So then let's move on. So we have seen that with the SR flip-flop, we can detect when the envelope has reached its peak. And now the question is, what do we do with that information? And the answer to that is basically that we are going to use this to get our our decay and sustain phases. And the way this works is, let me get rid of this for a second. The way this works is the following. So the voltage at this point here is basically what tells us if we have reached the peak or if we are yet to reach the peak, right? If the voltage here is high, we know that we're not at the peak yet. And if the voltage at this point is low, then we know that we've reached the peak. So that means we are now in either the decay or the sustain phase. And this is going to help us in the following way. So if I remove this here for a second and give ourselves a little bit of space, then we can do the following thing. We are going to take a potentiometer, like so, and we are going to set this up over here. And wait, let me give this a proper value. I'm going to give this 100K. And then we'll place this between a voltage source. So we go with our supply voltage, which is, as you remember, it's 12 volts. You can do this with any other voltage level, like whatever you want to use. You can use 9 volts, you can use 15 volts, doesn't matter. So we're going to set this up between 12 volts and then the output of our SR flip-flop. And let me get the analog output here so that I can show you what the voltage here is going to be. All right, I need to connect this again, and I need to connect this again. Whoops. Boom. All right, so why did I do this? Well, the idea is, if I reset this, I run this, oh, whoops, and we stop, right? Okay, so I forgot that I had set this already, but perfect, right? So I've stopped it. So we're now seeing a snapshot where we are still in the attack phase, right? We are still below 6 volts. So our SR flip-flop is still on because we haven't reached the peak. This means that the output voltage of the flip-flop is 12 volts, which is the logic high voltage, right? And this means that the attack phase is still running. And if we look at our potentiometer, the cool thing now is that we have got a voltage divider between 12 volts and 12 volts, which means that no matter where we set the wiper, we're going to have a 12 volts output. And this is interesting for us because, I think we'll get to that in a second. What's actually more interesting right now is if I let it run and then pause over here, right? So we can now see that since we've reached the peak, right, we're at 6 volts here, the SR flip-flop has turned itself off. And we can see that we now have 6 volts over here because this potentiometer is set to 50% at the moment. It's set to 50% at the moment. Whoops. Boom. And so we get 6 volts. And if we set this to a different level, we can get a different voltage out of this, right? So I can now vary this basically from 0 volts all the way up to 12 volts. And this is, or this will be, how we get our sustain level. Because we are now officially in the decay phase, or we would be if there was like a way for the cap to discharge. The decay phase, as we saw earlier, is basically just when the envelope the envelope voltage, the output voltage, drops to the sustain level, right? So with this voltage here, we basically have a sustain level. So if we now were able to discharge the capacitor into this potentiometer, like to this voltage, then we would have a way to have a decay phase and a sustain phase. Sorry, this is very convoluted. This was more clear in my head. I hope this was clear enough. I think I'll just like keep building this, and then probably it's going to become more clear, like what I'm trying to do here. All right. So basically, what we want to do is we want to take the voltage that we have here, right? Because this is going to be our sustain voltage. And we're gonna want to discharge our capacitor into that sustain voltage. Now, to be able to do that kind of smoothly and like properly, we will want to buffer the voltage at this point, right? Because this is still like, this is a big potentiometer. This is 100K resistance, and so if we want to discharge to this voltage level, like to those, right now it's 4.3 volts. Then we're going to need to buffer this, right? Because we need the current to flow out of the cap and then kind of be sunk by something. And this potentiometer is a resistance, and so it can't really effectively sink voltage properly. So what we want to do is we want to use a buffer. For now, we're going to use an op amp because that's kind of easiest. So I'm going to put an op amp in here. And I am going to configure this as a voltage buffer, like so. Oh no, that's not correct. Boom. Gonna switch this over here, and then boom, and boom, and boom. And again, this helps us because now we have a buffered version of the voltage at this point. And this is good because we can sink as much current as we need into this op amp's output, and we won't have to worry about this resistance that we have here in this potentiometer. Right. Now, what we want to do is we want to actually go ahead and provide a path for the capacitor to discharge into this buffer. And I'm just going to go ahead and set this up over here. So we're going to pretty much mirror whatever we have here with the exception that, of course, the direction of the diode needs to change. And we need to make this fit in here. Let's see if this is going to work somehow. It doesn't really look like it. We can get this a little bit shorter. Boom, boom. Move this over here. Move this down. Alrighty, this should work. Oh, I've put it too far down. That's unfortunate. So it needs to go one up, and then this needs to go up two. Boom. And then the diode, like I said, so this is the wrong direction, right? If we want to discharge into the op amp, if I put it here. The problem is we couldn't discharge because the diode would be blocking it, right? Because diodes are one-way streets for currents. So what we're going to have to do is we're going to have to turn it the other way, like so. Boom. And now change this little label here. And we're going to change the slider text. Boom. And yeah, this should be it. So basically now what's going to happen is, well, let's start at the beginning again. So I'm going to run this. So switch it off, boom. All right, so this is state 0. Gonna turn this on and gonna pause it. So right now we are in the attack phase again, right? Because we haven't reached the 6 volts peak. So the SR flip-flop is still turned on and the capacitor is still charging. So the voltage here is still rising. And as we can see, since the voltage down here is 12 volts and the voltage down here is also, voltage up here is also 12 volts, the output of the buffer is also going to be 12 volts. So whenever we're in the attack phase, this node here will sit at 12 volts simply because, simply because this is high. So that's what I meant earlier. Like that's why this is important, that this voltage divider always gives us 12 volts whenever we're in the attack phase, because now no current can flow into the buffer simply because the voltage on this side is higher than the voltage on this side, right? We're still charging the cap. Right now we're at 4 volts, and 4 volts is lower than 12 volts, and so no current can flow in this direction. So by setting it up like this, we make sure that during the attack phase, there's no way for the current to leave the capacitor or for current to kind of like flow somewhere else. This takes care of the fact, or takes care of that basically, right? Okay, so let's keep going. Boom. Okay, so now we've reached the decay phase, basically, because we went up to 6 volts, the SR flip-flop turned itself off, and since the voltage here is now 0, since the flip-flop is off, we have a voltage here that is below 12 volts, because that's what I set the sustain to, right? So the sustain right now is set to 4.4 volts, and this is lower than the 6 volts that we peaked at, right? So if we peak at 6 volts and then the voltage here is lower than 6 volts, then what will happen is that we'll see a current flow out of the capacitor through this decay potentiometer, through this diode, and into the op amp buffer. And this will keep going. So current will keep flowing out of here and into the op amp until we've reached, and this is going to take a long while now because, diodes, they conduct less effectively the smaller the voltage difference across them is. But yeah, you can see that this voltage here, which is also our output voltage, maybe we should visualize this here. Boom. So this output voltage is dropping down to the voltage that we've set here, these 4.45 volts. You can see that it's getting closer and closer and closer. It's going to take a heck of a long time till it gets there, but yeah. So basically what we've implemented now with this circuit is we have the key down event. We charge the capacitor. We reach our peak. And then after we've reached the peak, we discharge the capacitor down to the sustain level, right? That is what happens here. Right now we're now effectively at the sustain level. Right, and even if I let go of the key now, nothing happens because we haven't implemented the release. But yeah, so with this little addition, we already have the decay and the sustain phase. So sustain, this potentiometer, and then decay is this potentiometer. That's it. That's all we need for that. I'm going to check the chat if there are any questions. Labskater Pussy says, isn't 12 volts kind of high for a gate signal? Isn't 12 volts going into VCA CV input pretty high? Are you talking about this? If so, doesn't really matter. Like, yeah, just using 12 volts here, we could use a lower voltage. The flip-flop would react to a 6 volts gate right now, but we're going to get to that later on. Right now, it's not really important. And then Alex says, if you take the buffer feedback after the diode, it will buffer the voltage after the diode. Yeah, I think you're right, but I actually have a better idea. I've been accused in the past of using too many op amps. So in this instance, actually, I'm very proud to say that I found a way to get rid of not only this op amp, but also this diode. We can actually put something simpler here, which saves us components. So, and there's always a good thing. And that thing is a PNP transistor. And I'm going to set it up, and then I'm going to explain to you why and how that works. So let me get a transistor. We'll get a, where is it? PNP. There it is. Oh no, right. First I delete these, and then I get my transistor. Boom. Okay. So the way that we're going to do is we're going to connect the base to our sustain voltage. We're going to connect the collector to ground, and then we are simply going to, let me make this look a bit nicer. Boom, over here. All right, and all right, good. Right, if you're now wondering why the hell I did this, oh, this is annoying. I can't really figure out why the like the flip-flop somehow starts, or sometimes starts at the high state, and I don't know why, but no matter, we can kill it. Okay, so if you're not asking why this is equivalent, which it is, I forgot to mention, like this is equivalent to what we have had before, basically. And the reason that is, and you know, we need to go a little bit into details on the PNP transistor here. The reason this works is a PNP transistor allows for current to flow from emitter to collector, in this case, if a small current can flow into the emitter and out of the base. So this means if we set the this voltage over here, this one over here, to 12 volts, then it means that in our scenario, like because our voltage here peaks at 6 volts, there can never be a voltage that actually flows into the emitter and out of the base, because the voltage at the base is higher than the voltage at the emitter, and thereby it's blocking the connection to ground. And that is why, in that case, we can't have a current from the capacitor into ground. But, oh wait, let me prove it to you first. Right? Let's try this. So I've set this voltage to 12 volts, and I'm going to engage the switch here. So this goes high, capacitor gets charged, reset input gets triggered, flip-flop turns off, but our capacitor does basically not discharge. It discharges a bit because, you know, we're simulating, leakage currents. But yeah, nothing is really flowing on this path. And that is because the voltage here, like I said, is higher than the voltage here, which means that the transistor is turned off, which means that no current flows between emitter and collector. But if I now turn this below the level at which the voltage here sits, right? So this is now at 3.5 volts, and this is at more than that. Oh wait, let me try this again and make it a bit more clear. I think I can make it more clear. So up to 12 volts again, turning this on, we're charging our capacitor. All right, and now I will turn down the sustain, and we can see that now current flows through the transistor. And that's because the voltage here is higher than the voltage at the base, which means that a current can flow into the emitter and out of the base, which allows for a much larger current to flow into the emitter and out of the collector, which discharges our capacitor, right? So we can see now that it's kind of like stabilizing at 2 point, what is it? Yeah, I'm not sure if it's going to go down all the way there. Like there's going to be a little bit of an offset, but actually we don't really care about that, I think. Let me try and turn this completely down. Let's see how far we go down. I should probably turn the decay down too, so it's a little bit quicker. Okay, so we might actually stay at a diode drop before ground or before 0 volts. Not entirely sure, but still, in my books, this is a worthwhile simplification, and I pretty much like it. So, and yeah, it's still falling, and yeah, this simulation is very, very slow, so this is not real world speed. So, in practice, this drops much faster. All right, let me check if there are any questions about this. Okay, so Paul says, I find when I'm playing with envelopes in this app, it is useful to disable the vertical autoscale of the graph so you can see the range better. I think I have. Yeah, I have disabled the max scale. It still does it. It's a bit annoying, but I hope we can cope with it. All right, so now with this simplification, we basically have, again, our attack phase, we have our decay phase, and we already have our sustain phase. So the only thing really left to do now is we need to implement a release phase. Let me pull up a different version of this one that is a little bit neater. Oh, wait. I forgot like a really important thing. It's not really obvious. It's something that I worked with this design for a while, and very late I kind of realized that there's actually a problem with this, which in this version is not addressed. And I'm going to show that problem to you in the simple version of this one. Let me jump over here. All right. So the problem that I'm talking about is a kind of scenario that we haven't thought about, which is the following. So with our peak detection, right, what we rely on is the fact that this capacitor gets charged up to that peak level, and then this thing turns off, right? That's how we implement it. But that assumes that our button stays pushed, right? So we're working with the assumption that the key up event is way, way, way later in the ADSR's life cycle, right? We assume that's going to be like during the sustain phase. And so we worked with the assumption that we press the key and then we just run through the attack phase until we hit the peak. Now, the scenario that I'm talking about that we need to address is, what if the key is actually released during the attack phase, right? What if the user presses down here and then releases the key over here? We've never reached the peak, right? In our scenario over here, or in our circuit over here, we're not accounting for that, right? So if I press the key and then release it instantly, the flip-flop is still on, right? Because we haven't reached the peak. And so wait, let me make this more clear. I will increase the size of this dramatically. Boom. Right. Okay, I'm going to do this again. So I'm going to press the key. I'm going to release. You can see I've released the key, but our flip-flop doesn't care, right? Our flip-flop still says, well, I'm going to charge this capacitor until we've reached the 6 volts. Because that's, that's what this circuit is basically designed to do. Like, it's designed to charge until we've reached the peak. But in our scenario, actually, that kind of behavior is not really what we want, right? Like in an envelope generator, what you want is, if we release the key during the attack phase, we want to enter the release phase. That means we want to skip the decay and the sustain phase, and we straight want to go into this and drop the voltage down again. With our circuit here, not really feasible, right? Because this will keep trying to charge the whole time, right? Because that's what it's designed to do. So we need a way to make this flip-flop turn off whenever the key goes down or up, however you want to see it, right? So that's what we need. We need a second mechanism that resets the flip-flop whenever the key goes up. And now to do this, we could work with this simple SR flip-flop. We could keep working with this. But I've actually found an easier way to kind of implement this with a little bit more complicated type of flip-flop. And that type of flip-flop is called a D flip-flop. And conveniently, the circuit simulator actually has one of these in here. If we go to digital chips, we can find the D flip-flop over here. All right, I'm going to draw one up here. And I'm going to change, let's change to this. And let's give it a set and a reset pin. I'm giving it a set and a reset pin simply because the D flip-flops that I have, like I have a CMOS chip, it's called the 4013. It is a CMOS D flip-flop, and or it's a dual flip-flop actually. And those flip-flops, they have a dedicated reset and set pin. And so the set and the reset pin we already know, right? We also already know Q and Q with a line over it. So Q is the output and Q with a line is the inverted output. So we know these four. We know the set, reset, inverted Q, and Q because those map to set, reset, Q, and inverted Q. We know those. Now the new things that this adds is a clock input. That's this one. And then a data input, that's this one. And the way that we're going to use these is a little bit unorthodox, or not really like how it's meant to be used. So yeah, this is meant to be used in a very specific way, and that is as a clocked flip-flop. So I'm going to quickly show you like what that means and how that would work. So if we add a clock signal here, which is going to be a simple square wave. Boom. All right. I need to give this a proper duty cycle. Let's make it 50. Right. So you can see here, I'm just sending in a square wave, which is a clock, which is clocking the chip. And now what the chip basically does is every time the clock goes high, so every time this line goes green, the chip will look at the data input, and whatever voltage is applied to the data input will be what the flip-flop kind of saves as its state. So if we give this a, whoops, oh no, let me do this a little bit more easily. No, that's not right. I think it's this. Yes. Okay. Let me switch this down to 0 volts. Okay. So what happens right now is every time this clock goes high, the chip looks at the data input, sees that it's 0 volts, so ground, and that's why it sets its state to off, right? This is why this stays off. The output stays off. But if I switch this up now, I bump the voltage up to 12 volts, then it should actually switch on, but it doesn't. Oh, I think the clock is not strong enough. Yes, I think we need to bump this up to 12. Right, okay. I was panicking there for a second. Right, okay, so you can see now that the flip-flop, when the clock went high, looked at the data input and set itself to the on state. If I drop this down to 0 volts again, you can see, boom, there it goes. So whenever the clock goes high, it looks at this thing, and then it sets itself to whatever is currently applied to the data input. Now, if we put in a triangle wave here, for example, we're going to give it 12 volts max, and we're going to give it maybe 40 hertz is fine. Let's see what happens. What What's the voltage? 12. Doesn't register. Strange. Let's give this a little bit of a slower frequency. Let's bump the frequency of this thing up. Let's see what happens then. Oh yeah, now it does. Now it works. Okay, now you can see that whenever the clock goes high and this triangle wave is high enough, it's switching state to on, and then the opposite happens if the triangle is low, basically. So this is how that works. And the set and reset are kind of just an added a bonus to this chip, or to this flip-flop in this chip. And you know, it's just present there, but normally a D-type flip-flop is just these two inputs, and this is how it works, and this is what it's normally used for. Right, so the first thing that we'll do now is we'll go in and we will simply take our circuit that we had up here, this one, and we're going to replicate this with the D-type flip-flop. And here's how we're going to do that. Wait, let me check the chat for a second, if there's any questions. Lapskater Pussy says, if you were to change the 12 volts to 6 volts on the transistor part, wouldn't that let you use the full range of the part to choose sustain? Yeah, that's true. We're going to get to that in a second once we've like defined the peak voltage level. Bastionix, out of curiosity, could you do a video or live stream on how to make a kick module? That's on the agenda. I do want to like down the road do percussion. Justin says, hey Moritz, meant to toss this in the Patreon post, but check out the envelope generators in the Roland GR500 for an example of a design that uses logic gates to control the stages. We'll check that out. Paul says, from memory and the properties of the graph, you can set the vertical axis min and the max values manually to 0 and 12 volts or whatever range you want. That should fix the range. Okay, cool. I'll try that in a second. Good. Then let's get back to the simulator. I hope that you can see this, because in my preview here, oh, it's just severely behind. Interesting. Oh, all right. Okay, perfect. Panicked there for a second, but yeah, okay, you can see the simulator. Right. So what I've done here is I've taken our previous circuit, which is the charge until peak, and I've simply replaced the flip-flop that I made from the logic gates with this D-type flip-flop, which again is the 4013 version of a D-type flip-flop. And this circuit is functionally identical to what we had before. So we have the input here, we have the high-pass filter connected to the set input, and then we have our output, which charges the capacitor through a potentiometer, and then that capacitor is connected to the reset input, and that resets the flip-flop whenever we hit the peak. Okay, so let's try this. Going to discharge it, gonna turn this on, and we charge, and we have reached the high threshold, and so this turns off. Boom, perfect. Okay, so this works exactly the same way as we've seen before. All right. And now what we want to do is we want to implement what I just described. So we want to implement that whenever we let go of the key while we're still in the attack phase, we want to toggle the flip-flop off, right? And the way that we're going to do this is we're going to abuse the data and the clock input. And we're going to basically abuse them and make them into a second reset input, because this one is already used for this, and you know, with some trickery we could use the same one, but this is much easier, like abusing these as reset inputs. And the way that we're going to do this is, first up, we're going to hardwire the data input to ground, right? And so now whenever the clock input gets a signal, it will toggle the flip-flop off, right? Because it's gonna put whatever data is on the data input into the flip-flop. If this is ground, it's gonna turn it off. Now the problem is the clock input always kind of registers a clock if the voltage rises from 0 to or above the threshold. So in our case, it would be, it has to rise from 0 volts up to at least 6 volts. But the issue is that our key press event, or rather our key down event, does not produce like an upward spike, right? Like if I switch this off, then we basically, we could just get 0 volts at this point. But we need a rising edge to trigger the clock. So that's a bit tricky, but there is a really simple little really simple little circuit that we can set up that actually takes our event here, takes our like going down from 12 volts to 0 volts and converts it into a rising edge, which then we can use as a clock. And the way that this works is we take another capacitor. We're going to set this up. Wait, let me make this a little bit smaller. Boom. We're going to set this up over here. We're going to connect this to our key here. And then we are also going to connect this to our clock input. Right. And then we are going to use another resistor over here. I'm going to use 100K. And oh, this is a little bit ugly. Let me try and fix this. Boom, boom, and all right. And then we are going to apply 12 volts at this point. Right, and this might seem a little counterintuitive because this looks like a high-pass filter, but instead of having 100K connected to ground after our capacitor, we have 100K connected to 12 volts. And what this does is, whenever our key here is low, like when we have 0 volts at this point, we're going to have 12 volts at this point, right? Well, let me put this in the scope. So we're going to have 12 volts here, simply because this is connected to 12 volts. There's nothing coming from this side. So this is just, 12 volts. Right, and now let's see what happens if I toggle the switch on. Boom. So we're getting a spike that goes upwards. I'm not like, sometimes the simulator is weird. I'm not sure if this would actually also happen in real life. But since it's just a tiny spike, like even if it did happen, it wouldn't fry our chip because it's like such a short little burst. So that's fine. But we don't really care about an upward spike, right? That's like from 12 volts up, the chip is not going to register it, because for the chip to register it, it has to start at 0. It doesn't start at 0, right? Now, if I release the key, we can see that in the second that this drops down to 0 volts, basically what happens is that suddenly the pressure, if you will, coming from this left side is released. And this means that for a split second, current can kind of like flow into the capacitor, right? Because the pressure here drops, so we have a little bit of room to like jam current into this capacitor. And because we have a resistor here, for a very, very short second, the voltage here actually drops, and it drops to 0 volts, interestingly enough. Like, because we have 0 volts here, we take the pressure off of the capacitor and the voltage here drops to 0. And then very, very quickly, obviously, the current will come from the positive supply rail, squeeze through the resistor and fill up, the capacitor again. But for that split second, we go down to 0, and then we quickly go up to 12 volts again. Let me reset this so we can see this again. So boom, high spike, and boom, low spike. Again, reset this. low spike, no, high spike, and now low spike. Boom. And what this does is that it triggers the clock input. So basically, when we release the key, we will have a clock event coming in here, which will tell the flip-flop to look at the data input, which is tied to ground, so it's always low, which means that the flip-flop is going to turn itself off. And that is how we make sure that if the key up event happens within the attack phase, the envelope will actually start entering the release phase, right? Because in that moment, like when the flip-flop turns itself off, this means that the capacitor no longer gets charged. We can enter the, in our case, actually the decay, sustain. Oh, we're going to get to that in a second. But yeah, so this turns off. So basically, we turn off the flip-flop before we've reached the peak, which is exactly what we set out to do. So yeah, and that is why we need to use a D-type flip-flop. It's basically just to have two reset inputs. That's all that is. It sounds very fancy, but that's all we use it for. Right, and with this in mind, we can actually get back to our decay and sustain phase. So let me pick this up over here. All right, so this is basically the combined version of what we just had, what we just kind of put together, and what we had before with the decay and the sustain. So let me reset this. All right. So just to explain this, we still have, we still have our input key here. We have our high-pass filter that is connected to the set input. We have our little weird kind of, it's not, I'm not sure if I think it is a high-pass, but it's like a high-pass that generates a upward slope on key down to the data, to the clock input, data input tied low. These things just reset the flip-flop whenever the key goes up. And then we have our attack phase here. So we go through the output, through the pot into the capacitor. Then we have our oh wait, I added the buffer. Oh no, this is way too advanced. Sorry, ignore the buffer, ignore all the things, please. Right. I'm gonna take these out for a second. Boom. All right. Go in here and like that. Boom. Boom. Okay. This is what we had before. Right. We charge through here. Once we've reached the peak, this flips off, and then we discharge the capacitor through this pot and through this transistor and to ground. That's how that works. Let's try it again. I'm going to have to monitor the voltage here. I'm going to try the tip that someone gave me in the chat. Manual. Oh God. DC coupled. I don't really care. Does this work now? Okay. This doesn't work. Ugh. Okay, I'm in the interest of time, I'm just going to go back to auto. Oh, maybe this? No. Yeah, who cares? All right. Let's see if this works. I'm going to turn down the sustain a little bit, and then we're going to trigger it. Oh no, we need to discharge it first. Reset. Okay, trigger it. All right. That didn't really work. Why does it not work? Oh, well, I need to lower the sustain level more. Alrighty. Reset this again and try it again. Boom. Attack. Okay. Attack, decay, and then sustain. Right? Attack, decay, sustain. Perfect. Let's turn up the attack a little bit. Like so. Dude. Ugh. Discharge it. Boom. Okay, so now let's try and see what happens if we turn the attack way up and then we trigger this. Oh. Oh. Why is it so short? I would have expected this attack phase to be much longer, but it's super short. I don't know why. It's already 1 mega ohm. All right. That's just how it is. I think I need to bump up the capacitance here so that it takes longer for the capacitor to fill up. All right, let's try this again. So attack phase, and then we skip the attack phase. Boom. And yeah, it does turn off. So perfect. Now, the two things that you just saw me delete, we should add back in. So someone in the chat already mentioned that we kind of have the issue here that the peak is 6 volts. Our sustain level goes up to 12 volts. So there's a bit of a kind of, there's a big dead zone in this potentiometer. And then also I said in the beginning that normally a Eurorack ADSR will peak at around 8 volts. And so we should make sure that it does that, because at the moment our envelope peaks at 6 volts, right? If we try this again, boom, we can see that the peak level is 6 volts. Come on. Boom. Yes, it's 6 volts. That's when the reset input triggers. Now, to get that higher, basically, we just have to make sure that the voltage at the reset input is lower than the actual voltage at the envelope's output, right? And to do that, we can simply use a voltage divider. Now, the problem with that is if we simply add in a voltage divider over here, like, wait a second, like so, boom. Let's do a 62K, and then we do 100K over here. Boom. So now if we had 6 volts and we applied them to this voltage, not 6 volts, if we had 8 volts and we applied them to this voltage divider, then you can see that, oh, that's actually much lower. Interesting. Let me try with the lower resistance value. Yeah. 42K, I'm guessing. Oh God, even lower. Interesting. 39K. 33K. Yes. Okay. So with this voltage divider, we only get 6 volts at the reset input if our envelope's output sits at 8 volts, right? So that's how we kind of increase the peak. Before it was 6 volts because we didn't have a voltage divider here. Now with this voltage divider, the flip-flop would shut itself off at 8 volts. Which is what we want, right? Now the problem is I cannot simply tie this point here to this voltage divider, because this would allow the capacitor to discharge to ground, right? Because we have a path to ground here. So we cannot simply just wire this up. So what we need to do is we need to buffer the output of our envelope. And we do that with an op amp, because that's the simplest solution for buffering. I'm going to set this up over here. Let me adjust the voltages to be in sync with everything else. And then we're going to take this output and we are going to run this over here. Oh God, yeah. That's a short circuit. You shouldn't do that. And good. Add an output. And boom, all set. Now it should peak at 8 volts. Let's see if it does. And 5, 6. I should reduce the size of this cap. 7. Boom, 8. And that's where we enter the decay phase. Let me turn this down a little bit. Boom. Okay, try this again. Attack, decay, sustain. Perfect. Good. So that's how we change the peak. Also, if you wanted it to be like much bigger, you could also do just a 100K voltage divider, and by doing that, let me me show the peak voltage level here. Boom. Yeah, you can see that now it peaks at 12 volts. So this voltage divider is for you is the control how to define where the envelope peaks. In our case, we want to do this, so that it peaks at 8 volts, which is the kind of standard. All right. Now the only missing piece is the release phase, right? So we wanna be able to, like, after we've entered the sustain phase and the user lets go of the key, we need to have a way to discharge the capacitor like down to 0 volts or close to 0 volts basically. And thankfully this is really rather easy. All we have to do is, wait, let me rearrange this a little bit. Boom, I'm going to turn this over here. And like that. So all we need to do is we need to say, okay, so what is for us the indication that we enter the release phase? If we go back to this diagram, we can see that what indicates to us that we're entering the release phase is the key up event, right? If the user lets go of the key, or if the gate goes off, then we want to enter the release phase. If we look at this in the simulator, no, that's the wrong one. Bye. If we look at this in the simulator, then we can see that we have the information about the key state over here, right? Before these two capacitors. Like this voltage here is what the state of the key is. If this is high, if this is 12 volts, the key is pressed. If this is low, the key is no longer pressed, right? So what we can do is we can simply say we're going to take we're going to create another path coming from the capacitor, coming from this point. We're going to set up another potentiometer and a diode. Thing is, the diode needs to point in the other direction. Boom. We're going to call this our release pot. And we are going to wire this just straight up to the gate input. And as you can see, it's already discharging. And the way this works is, if this key is pressed, boom, then the voltage here is going to be high. We're going to have a high level voltage, 12 volts in our case. And that means that this diode is just pressed shut, right? Because the voltage here is the highest voltage that we have in our system, 12 volts. And that means that nothing will flow out of here simply because we've closed it, right? And now if I keep running this, we can see that we run through our attack phase, our decay phase, and now we're in the sustain phase. And still, the capacitor cannot fully discharge, like it can only discharge to the sustain level because this diode is still blocked, right? Because the voltage here is still 12 volts because the key is still pressed. But if I let go of the key now, then the capacitor is allowed to discharge through this potentiometer, through this diode, and into the input. And that's it, basically. That's the whole envelope generator. Again, let's run through it. So, decay, attack, decay, sustain, release. Let me turn this up a little bit and run through it again. Attack, decay, sustain, and release. That's it. One thing I just noticed is someone mentioned in the chat that you know, we don't use the full range of this, and it's still true because the peak value of our envelope is now 8 volts, but the sustain can go up to 12 volts. So that means there is going to be a significant dead zone in the potentiometer. Off the top of my head, I don't have like a really good solution for this right now because like specifically getting 8 volts here is going to be a bit of a pain. So I think I'm going to be okay with the dead zone for now. Maybe for the proper video release, I'm going to have a good solution here. But maybe someone in the chat has an idea. Use the scroll. Oh yeah, I don't have a scroll wheel, Justin. I'm using a mouse pad, so I'm not sure if that works. Ian says, just curious, if you're going to put an op amp at the end, why not just use that to amplify the output a little rather than do the whole voltage divider to reset thing? Well, basically because you do not want the output of the envelope to be super high, right? You want the output of the envelope to be 8 volts at max. That's the standard. So it's better to divide it down at the reset input than to increase the gain of the op amp. Burak says, you can also change the timescale of the scope when hovering above it using the mouse wheel. Again, I don't have a mouse wheel, I'm sorry. Okay, and then AKA Nerd says, hello, isn't the reset pin be triggered with a lower voltage than 6 volts? What's the logic? Yeah, so the way that the CMOS IC behaves that I have, the 4013, is that it registers half of the supply voltage as a high-level voltage. So in my case, I'm using 12 volts as a supply voltage. So 6 volts is the threshold when it registers a logic 1. That's 6 volts. And then this yes, this is this CMOS chip can work with more than 5 volts. It can actually work with 12. I think even with 18. I would have to check that out again. All right. What else? Cash German says, I knew I kept a box of 40 series ICs around for something. Yeah, they're all pretty good. They're all pretty nice. It's really good. And then Dabroni says, why can't you use a voltage divider before the sustain port? That might actually work, right? We could maybe just put a resistor here, I guess. If we put one here and we give it like 33K, then I'm guessing the highest voltage will be, now it's 9. So we need to give it a little bit more. Let's try with a 47K. Right, now it's 8. Perfect. Yeah, good suggestion. It's not a voltage divider. A resistor is enough, right? Because now even if I turn the sustain all the way up, like we still have a resistance here, which means that we're not going to have 12 volts here, but instead around 8. So this is the fix for that. Thank you. Very good. Boom. Oh yeah, someone said you could add another resistance series with the potentiometer. Did that. Good. Steiner says, for fixing the dead zone, I think it's the same suggestion. You could add an extra resistor. Yeah, yes. Very good. And then Labs Get a Pussy says, aren't sequencer gates usually 5 volts? So couldn't you have a scenario where the capacitor is discharging because the sustain level is higher than the gate blocking the diode? Don't really get that question. Aren't sequencer gates usually 5 volts? Oh, you mean at the input? Yes, we want to treat the input so that they are going to be high enough, right? So yeah, we need to think about the fact that the gate could be lower, but we'll do that in a second. James says, what about a 33K and 68K potential divider at the sustain port to provide? Yeah, just did that, so it works now. All right, so then let's address this question with the gates at the input, because that's a valid concern, right? Because right now we are assuming that our input gate is going between 0 and 12 volts. That's kind of an ideal scenario. And why is it ideal? Well, because if the high level voltage is 12 volts, and that means that our release path will be blocked whenever the key is pressed. But it's true if this is just 5 volts, which is common in Eurorack, right? In Eurorack, you often have a situation where a sequencer will put out 5-volt gates. Then we would have the following problem. So we engage this, and as soon as... Oh, is it even worse than I thought? Why is it not charging at all? Oh, right. So this won't work in the first place simply because the flip-flop will not register this as a logic 1, right? I just explained that the CMOS will only register this as a logic 1 if this is 6 volts or higher. So you would have to bring this up to 6 to actually see any effect here. So let's try this again. Boom. Oh, still 6 volts, it doesn't register. Interesting. So we probably have to go even a little bit higher to make this here spike at over 6 volts. Let's try this. All right, so this worked. So now we're already at 8 volts, and we don't see the effect where the cap is discharging here. But yeah, nevertheless, you can see that it's very important that this gate is strong enough to actually trigger the flip-flop. So we have a couple of options here. Now, if we want to go like really super clean, what we would do is we would use a comparator over here to kind of take the input gate, and then the comparator would compare the gate to a threshold, and we would set the threshold at whatever, like 3 volts. And whenever we go above those 3 volts, comparator would push out a high level voltage, and that would be fine. But then the problem is whenever the comparator switches into the opposite state, so when the input voltage is below the threshold, it will go negative. And this is annoying because we don't want negative 12 volts, but instead we want ground. And this is a problem that I'm running into a lot in these synth builds. And usually the solution is to use a diode and then use another buffer. But this is kind of wasteful. And so in this case, I think we can get away with a kind of simpler, if a little bit rougher solution. Here is what I'm kind of proposing, or what I've tried and what works. We can use an op amp, and we can use it simply in the configuration as an amplifier. Here's how that works. So we are going to give this a little bit of gain, and I'm going to do a gain factor of 2 for now. So we achieve this if we put a voltage divider on the feedback path of the op amp. And if we use 2 resistors of the same value as I'm doing here, then the gain of the op amp will be 2. Let me show you that. So I'm going to put in a voltage source here, and then we're going to have a look at the output over here. Boom. Now this is 5 volts, and you can see that the output is 10 volts. And then what we are going to do is we are going to put a diode in front of this. Whoops, over here. And we're going to use another 100K to ground over here. And then we are going to set up a little input signal, and we're going to make this a square wave, and this square wave is going to oscillate between 5 and -5 volts, right? Because we want to be prepared for the situation where the input gate does not drop down to ground, but maybe it drops down to a negative voltage, and we want to be prepared for that. So we're gonna assume that we have a +5 -5 volts clock here. And as you can see, what happens is whenever this clock is high, the diode conducts, the voltage here goes up to, a bit below what we have here at the clock level. And then our op amp is doubling that voltage. So, it's almost going up to 10 volts, yeah. And if it goes below 0 volts, then basically the diode blocks. We have 0 volts here at the input, and the op amp drops down to ground level. And this is, I think it's an okay solution, right? Because this will work with most clock signals that are at least, what do we need? 4 volts. You could increase the gain if you want to, but for Eurorack level gates, this should be okay. And this is also safe if the input is much higher. Like even if we have 12 volt gates coming in, this will never go above 12 volts simply because we supply the op amp with 12 volts. So this is fine, right? So unless anyone has an objection, please put it in the chat why you shouldn't use that. But I think for this purpose, this is actually okay. So let's wire this up to our circuit here. And I think we need to, to make this look a bit nicer in here, I think we have to drop down the value of our capacitor. Right. Okay. Let me set the sustain level. All right. So there's our nice little ADSR shape. You can see the attack, the decay, the sustain, and then the release at the end. And also, this little fix prevents the release path to be active before its time, right? Because if we have a valid clock here, then the voltage here will always be high enough to block this diode. And that is basically it. Let me check the chat if anyone has a better idea for the trigger. Let me check. Burg says just add a switching transistor at the input. The problem is we need to sync current, right? You could theoretically, you can set up something with transistors, but you would have to use two, and you'd have to make some compromises to be able to sync the current coming through the release path. Yeah, the op amp is just the simplest solution in this case. Justin says you could use a rail-to-rail op amp for the input comparator and the negative supply voltage to ground instead. Yeah, I could do that. The thing is, I only have TL074s here, and they are not rail-to-rail, so I would have to get them specifically, and yeah, it's an option. I'm not too fond of it. Cash Garmin says, could an NPN transistor work with something like this? We can get into that in a second. I'll get back to this. Half God, half B says run comparator between plus rail and 0 volts. That won't work simply because if I use a regular op amp, regular op amps cannot drop down to the negative supply voltage. So if you give it 0 volts, it cannot go down to 0 volts. It will be stuck at something like 1 volt or 1.2. So not ideal. Burek says you would need 2 NPNs. Correct. We're going to look at that in a second. Ian Cox said, not that I would ever endorse using an op amp as a comparator, but listen, I've got a lot of LM358s around. All right. Cash Garmin says, I would love to see that implementation because I'm not sure I understand. Burek. Yeah, I'm gonna get to that in a second. Then Labs Get a Pussy says, if you look at the René Schmidt's ADSR design, they use that for gate 2 with 2 NPNs. Yeah, we'll get to that. Warpix says, could you use a transistor for this purpose? Yes, we'll get to that in a second. First, I want to show you that the circuit actually works, and I hope that I can switch over to this. Right, I hope that you can see this. So to save all of us a little bit of time, and to kind of show you that it actually works and how it sounds, I've already set this up. This is the exact circuit that I've shown you in the simulator, the last one, this one. There's one little alteration that I've made here, which is I've put a resistor here. And that is very common practice with envelopes. The thing is that if you don't put a resistor here, and if you then dial back the attack and the release completely, you will get these ugly clicking noises in the output of a filter, for example, because you turn it up and down too quickly, and that causes like weird clicking. And if we put like a very small little resistor here, like a 220 ohms, then that means that charging the capacitor up will always take a little while, and that way you kind of prevent these weird little clicking issues. But that's the only thing that is different here on the breadboard to the simulator. Right, and the way I've set this up here is we have attack, decay, release, and over here is the sustain level. And then I have also added a little status LED. That is done the same way that I've done it in my previous envelope video. It's just driven by a transistor. It's just to show you like the state of the envelope. Then I have wired it up to my modular, and over here there's a little push button, and this push button acts exactly like the push button that I've just shown you in the simulator. I've just connected it to 12 volts basically, and whenever I push this button, we apply those 12 volts to the input op amp, the one with the gain, and that fires the envelope. And here's what it sounds like. Let's hope it works. Right. So I think you can very clearly hear the 4 phases, right? Once I push down, you hear the attack, it swells up, then it reaches a peak, it drops down to the sustain level, and then when I let go, you get the release. Can you hear that? I hope you can hear that. All right, I think you can hear that. Let me mess with the controls a little bit. So here's what happens if I turn down the attack completely. So now we instantly go to the peak, then we drop down. During the decay phase, we drop down to the sustain level, and then when I let go, we go to the release. All right, next let's try turning up the attack all the way. And I'm going to let go of the button before we've reached the peak, right? That's what we stress so much about this situation, right? So let's talk about this. Yeah, it works, right? So I press, it swells up, I let go, it immediately drops down. See? All right, perfect. What else can we try? Well, turn down the attack, turn down the decay. Let's see how that sounds. Right. That's really weird. You hear this like clicking. It's like it reaches the peak instantly and it instantly drops down to the sustain level. So if I turn up the decay a little bit again, you can hear now you have like this little falling motion there. Right, and I can also turn down the release independently of the decay, which is what we were after in the beginning. So it instantly goes away when I let go. And this is like the thing that you need for acid basslines. You want to have like this instant hit, and you want it to like go down. You would turn up the resonance for that a little bit more. Oh, that wasn't the resonance. That was the pulse width. And let me find the resonance here. I need to turn this a little bit down. Yeah, a little bit more. Right, there is it. There it is. It's like the characteristic. Like this, like when the release is really short, but you have like this little decay down to a sustain level. That's like very characteristic for acid. I really like acid, and so I really needed like a device like this to be able to make acid basslines. So that was like my main motivation to make this. Right, and I'm very happy with it. I think it works pretty well. All right. Now to address the questions that we had. Right, so there was a question about if we actually need the op amp over here, right? Because would be great if we didn't have to use an op amp. Now the problem that we have, which I mentioned before, is this like whatever we use as a kind of comparator or buffer or whatever here has to be able to sink current, right? Because we want to be able to discharge our capacitor through the release path and into this kind of buffer. Now, what we can use as a comparator is we can actually use NPN transistors. We can set them up. Oh wait, maybe let's start one step earlier. Like we can use a transistor to get two very discrete states, right? And the way that this works, whoops, this was a PNP. The way that this works is that we set it up like so. We use a big resistance at this point. We use a voltage source over here. I'm going to use 12 volts again. And then we will need a resistance over here. A small one, or rather a big one would be better because we don't want to waste current. So we're going to set up a big resistor over here. And if we look at this now, we can see that even though this is just a 5 volts input clock, right? So we have 5 volts here. It's oscillating between plus and minus 5 volts. We get 12 volts and approximately 0 volts over here, right? The problem is that it's inverted, right? So whenever the clock is high, the output of this thing is low. And when the clock is low, then the output of this thing is high. The problem is we need the opposite. Like when the clock is high, this should be high. And when the clock is low, this should also be low. And we can achieve that if we simply set up another transistor like this. Because in essence, this is an inverter, right? So whenever the voltage here is high, the voltage over here is low. And when the voltage here is low, the voltage here is high. So this just inverts the voltage that we apply to the base. So it's safe to assume that we can simply take another one of these and set it up over here. And if we now apply the voltage from here to this transistor's base, then we should get the desired functionality, right? You can see that here. So clock goes high, this goes high. Clock goes low, this goes low. That's great. Now, and also, you know, this is just 5 volts, but the output here is actually 12 volts. So this kind of works like a comparator, if you will. Not really, but kind of. Now, the reason why we cannot really use it this way is that, I'm going to show you, if I connect this to our input, you can see that where before we actually were able to discharge the capacitor till it actually dropped down to 0 volts. Oh, wait a second. Oh, it doesn't work at all. Interesting. Let me check the peak value here. Oh, that's why. Right. So, but it's the same problem that I wanted to get to. So, the thing is, this flip-flop only triggers when the voltage at the set input goes above 6 volts. This solution has the problem that we have a big resistance over here, right? So we whenever this goes high, we if it's not connected to anything, we have 12 volts here, but because it's connected to these capacitors and current actually flows, like we don't get a 12 volt spike here. We get like a little tiny, not tiny, but we get like a little like 4 volt spike here, simply because we have a impedance here, right? So between the 12 volts here and the capacitors, there's an impedance, and so the current that flows through here is going to be limited by this resistor, and that's why we don't get the full spike. So what we can do is we can drop this down to, let's say, 10, and let's see what happens now. Right, so this, I think this is actually okay. Now the trade-off that I was talking about earlier, it's not super big, but the thing is, whenever this clock goes low, then we have kind of significant current flow from the positive rail to ground here, It's about 1 milliamp, right? Now I'm actually not sure like how that compares to what an op amp uses like when it's operating. But generally, like, we are seeing a bit of current waste here. But yeah, this is a very, very much a feasible solution to the same problem that doesn't use another op amp, right? So this way we could save ourselves an op amp. And actually, if the chip that I'm using right now on the breadboard houses 2 of these, so you could theoretically, if you want to build a module, you could build like a twin ADSR, with one of these chips with one TL072 and then some transistors to get this functionality over here. I hope that answered that question. I'm gonna go back to the chat and check for more questions. So Justin said, actually, does the comparator output need to go to 0 volts if the flip-flop won't switch until 6? The comparator output does need to go as low as possible to allow the release path to drain the capacitor as much as possible. So we do want to go down as far as possible. Anything else? More questions? Debroni left. Bye-bye. Cash Garmin says, what is the input signal waveform? It's a square wave, which is normal, like in your gate signal would be a square wave. James likes it. I'm very glad to hear that. Chase Griswold says, I'm just picturing Alchemy ADSR hold, attack, sustain, decay, release. So cool. Hold. This doesn't have a hold input. Hold control. Might be something for the future. What else? More questions. Oh, dude, there's a lot here that I didn't see yet. Chase says, I hate it when I can't get rid of the click even with a slower attack. Yeah, that, like in this case, it would be a matter of like increasing the resistance, the 220 ohms resistance that I put before the cap. Like if you just increase that slightly, go up to 470 or 1K, if you try it, you should be able to get rid of the click. All right. R.T. Schultz says, I'm studying for an electrical engineering degree because I fell in love with modular synthesis, and I must say that your videos are very helpful. Thank you. I'm very glad to hear that. Paul goes. Bye-bye, Paul. All right. I don't see any more questions. Oh, no. Kash Garmin says, is this basically a NOT gate? I think you're referring to the situation where it was just the single transistor. Yeah. I think it's actually, a NOT gate is an inverter. So, yeah. Adam says, why don't you use PNP transistor for this? For the same thing, you would have to specify. Chase says, this makes me sad. I'm stopping my specialization with analog, going down the Blackmagic RF antenna and microwave paths. Such a tough decision to make. I love them both. Yeah, sad to see you leave the world of analog. But have fun with the microwaves. Sauerkraft liked the live stream. Very happy about that. Thank you. Chase also liked it. Computing brains. Why do we hate op amps? We don't hate op amps. Op amps are simply very like they occupy a lot of real estate. Like if you, I had this problem a lot when I was working with Erica synths for the modules, where I was working on a circuit and I had a problem. I needed to buffer something, and I was like, okay, yeah, I'm just gonna add an op amp here. And then they would come back to me and be like, this doesn't fit on the PCB. We don't have space anymore. There's not enough space to put another chip on there. So yeah, the problem is that chips are just like big. They have a big footprint. So generally, like you want to minimize the number of op amps that you use. If you can use transistors, that's often better because they have a smaller footprint and you can fit more of them onto a PCB. So That's why we don't hate op amps, but we want to use them sparingly because you know, they need a lot of space. Labs Get a Pussy says this design is really cool. Seems easier to troubleshoot than the 555 ADSR. Yeah, I've also I've built the René Schmidt's 555 based ADSR in the past, and I had the problem with the 555 that it's like, I mean, I would have to look into it, but I didn't really understand what it was doing, and I didn't care enough to look it up. So that's why I went with this approach. Dave says, thank you for watching very much. Stana says, can you repeat the name of the SRD latch? Oh, the chip is the 4013. It's a CMOS chip, the CD4013. And then Sam says, another thing for the future is offsets and setting initial start and max attack level, like the old Yamaha envelope. Yeah, well, that's not that hard. We can do that. And then what else? Justin says, this seems like a cool design. I just picked up a few 4013s for sub-oscillator mod for my ARP Axis, so I'll probably build one of these. Cool. Yeah, let me know how it goes. Warpick says, what value for the potentiometers for ADSR? Oh yeah, let me put in the, so just that you have it, let me put in the proper values for all the components, because I kind of messed with these to make it look better in the oscilloscope down there. So, you know, you can go either with a transistor-based solution or with the op amp-based solution, doesn't matter. Right, so for the pots, these are all 1 mega ohm. Oh wait, this is really ugly. Ugh. Okay, so I'm just going to tell you. This is 1 mega ohm, this is 1 mega ohm, this is 1 mega ohm. For the sustain pot, I've used 100K. I think you could also increase it if you really want to, but 100K is fine for the sustain pot. And then this, I've had the best results with a 4.7 microfarad capacitor. That worked best for me. And then the 220K, 220 ohms resistor here worked well too. And that's it. And then, you know, if you want to tweak the peak level, you want to tweak the values here. This is for an 8 volts peak. If you increase the value of this one, you increase the peak. And that is basically it. Let's Get a Pussy says, wait, do you have the bill of materials for the one you have on the breadboard? I want to try building this. Yeah, so I basically, the values I just explained are the ones. I'm going to update the description, and I'm going to put the bill of materials in there. I'm also going to put the simulation in there. Basically all the steps, all the simulation steps I'm going to put in there. And then you can basically just build this yourself. Oh yeah, one thing about these, I would advise that you use logarithmic potentiometers here. Because if you use linear potentiometers, it's a bit awkward because the attack time and the decay time, the release time, they increase so quickly if you turn them up. If you use logarithmic pots, you have more fine control at the shorter end of the phases. That didn't make sense. You can dial in a very snappy attack, and you have a lot of resolution, in that area of the pot if you use logarithmic pots. Chase asks, I missed it, but what speaker are you running this through? No speaker. This is connected directly to the to my interface. I'm just using the envelope to control my modular, and my modular goes into my interface, and then you can hear this. Any more questions? Warpix asks, how hard would it be to make all the potentiometer values the same? I kind of hate stocking a bunch of different pots. You can just mess with the value of this capacitor, I guess. You could just make it bigger, right? If you want these all to be 100Ks, you could just make this capacitor bigger, and it should still work the same. The only thing is that, again, I would advise it to use logarithmic pots. You could also use a logarithmic pot for the sustain level, actually. So your call. But, yeah, if you want to make them all the same value, just tinker with this potential this capacitor value here. All right. Anything else? Kash Garmin says, is there any place for linear pots in analog synth? Definitely there is, because sometimes like for example in my filter design, the pot that I use for the control voltage, like for the big cutoff knob, that's a linear one, because the filter itself reacts exponentially to a linear increase in control voltage. So you want the control voltage to be linear, actually, to have like a smooth kind of cutoff sweep. So sometimes it makes sense. Birek says, I built a triple VCO with saw, triangle, and sine output with your oscillator core. Shared an individual CV for the oscillators. All SMD managed to fit it 70 millimeters wide. That sounds amazing, especially the sine output. I haven't worked on a sine output yet, so it's a mystery to me. But yeah, sounds really cool. Me build says, really cool design. My only concern is the clock rise and fall times. It shouldn't go above 5 microseconds according to specs, but it apparently works. Yeah, I think I do think it works. So far I didn't have any problems. Maybe I'm gonna run into some, but it seems very stable for now. Chase says, thank you for streaming this, so cool, been a fan for a while. Oh, thank you so much for watching, really appreciate it. Warpic says, could you post a link to this sim? Yes, I will post it in the chat right now. And then, if there's nothing else... Oh wait, that didn't work. Let me try this again. Boom. Copy it. And here it is. That should take you to the sim. Right. And then, like I said, all the other steps are going to go into the description. The bill of material is going to go in the description, but the stream will go private and it will only be on Patreon. So if you wanna rewatch it, you will have to go over there. Thank you so much for watching. I hope it was helpful for you. Oh, more questions. Vaporwave asks, do you have sims for any of your other circuits? I can't actually get a sim of your VCA to work for whatever reason. Yes, so if you go to the Erica Synths website and you go to the shop, you find the VCA in there, the DIY VCA. Oh, wait, I can just post the link here for you. Give me a second. So basically, these modules that I've developed with them, they all have manuals, and those manuals contain links to the simulations. So whatever you're interested in, you can just go to the shop page of that module, and then that shop page will have a link to the manual. Give me 1 second. I'm trying to multitask here. Boom. So here is the manual for the VCA. And if you go over here, then in each chapter, or I think almost in each chapter, you can find a footnote, and the footnote says, I've set this up for you in a simulator, click here to go there. And those links, they will lead you to the simulator. Yeah. All right. Then that's it. Thank you for watching. I am working on a new video. I will do a compressor. I have a design for a diode-based compressor that will be coming relatively soon. Apart from that, the Erica Synths manuals will also be released as a book. The thing is that we decided to extend the scope a little bit. So we want to not only have the manuals for the circuit design, but we also want to put in like patching tips and like just tips on how to use the modules. And so it increased the scope. It's going to take a little while longer. Yeah, that's also coming at some point. And that is, I think, all. So thank you so much for being here. Thank you for watching. Thanks for taking interest in this. I hope I could help you a little bit, and I will see you next time. Bye-bye.